Sanjana. This is our presentation for Refrigeration 1. The objectives for this experiment were to perform an independent review of a refrigeration system, model a system to determine the capabilities of the system, also measure the temperature, pressure, and flow rate at different locations in the system, determine the mass of the block, and determine the thermal resistance of the installation. This is the setup of our system. Figure 1 is a schematic of the system, and Figure 2 is a picture of the physical setup of the system. There's a flow sensor at each exit on the system. There are 3 pressure sensors, an accumulator tank, a refrigeration load, and a heat exchanger. The vortex tube separates the compressed airflow into 2 different streams, hot and cold. For the purposes of this week's lab, the vortex tube may be characterized as a function of the input pressure, P3. For part 1, we collected pressure, temperature, and flow rate data of the system. We were then able to determine the steady-state values and perform EPA to determine uncertainties. York regression was then used to determine relationships with the input pressure.
In the plot, you can see the actual gauge pressure of the air right before it entered the vortex for both the 50 psi and 80 psi cases. These steady-state pressures are very consistent, so we have a great deal of trust in the steady-state pressure values. On this slide, we have plotted the rest of our steady-state data. On the right are our vortex hot output temperatures and vortex cold output temperatures for both the 50 psi and 80 psi cases. 3 of these temperature readings are very consistent. However, the vortex hot output temperature for the 50 psi case fluctuates up and down quite a bit throughout the steady-state trial. Therefore, we can have a great deal of trust in all of the steady-state vortex output temperature values, except for the hot output temperature in the 50 psi case. As such, the 50 psi case data should be analyzed with caution. Finally, it should be noted that at the higher pressure setting, the output temperatures are further from ambient temperature in both the cold and hot directions. Also, on the left are our cold and hot mass flow rates for both the 50 psi and 80 psi cases. All of these steady-state values are very consistent, so we have great trust in these steady-state values. Finally, it should be noted that the higher input pressure setting led to increased mass flow rates and a larger difference between the cold and hot mass flow rate. Here we have performed linearized York regression to determine that the vortex cold output temperature decreases with increased input pressure, as shown in the plot. The red uncertainty ellipses suggest there is very little uncertainty, which is also suggested by the very small regression parameter uncertainties. Here we have performed linearized York regression to determine that the vortex hot output temperature increases with increased input pressure, as shown in the plot. The red uncertainty ellipses suggest there is very little uncertainty, which is also suggested by the very small regression parameter uncertainties, although from before we know that the 50 psi data point is potentially inaccurate. Here we have performed linearized York regression to determine that the cold output mass flow rate increases with increased input pressure, as shown in the plot. The red uncertainty ellipses suggest there is very little uncertainty, which is also suggested by the very small regression parameter uncertainties. Here we have performed linearized York regression to determine that the hot output mass flow rate increases with increased input pressure, as shown in the plot. The red uncertainty ellipses suggest that there is very little uncertainty, which is also suggested by the very small regression parameter uncertainties. On this slide, we have summarized the steady-state data and relationships. In the top table are our mean steady-state values for gauge pressure, cold and hot vortex output temperature, and cold and hot mass flow rate. As depicted by the arrows, the vortex cold output temperature decreased with increased input pressure, while the vortex hot output temperature and both mass flow rates increased with increased input pressure. Clearly, the vortex can generate more extreme hot and cold temperatures with higher input pressures, and increases in input pressure forces the air to flow faster, which makes intuitive sense. In the bottom table are the uncertainties of the mean steady-state values at an uncertainty level of k equals 2. All the uncertainties are very small compared to the values in Table 1, potentially suggesting our data is accurate. Also, the uncertainties didn't change much from the 50 psi case to the 80 psi case, although it should be noted that the mass flow rates exhibited the largest changes in uncertainty of the shown parameters.
Thank you, Matt. Now we'll be introducing procedure and results for the analysis specific to the refrigeration load. The same data collected at 50 and 80 psi was then used to determine the thermal resistance and mass values. The thermal resistance was found using the steady-state data, and the mass was found using the transient data, both relying on reordering the energy change equation. The theoretical thermal resistance was found using the surface area of styrofoam that was in contact with the block. This was found to be 28.28 Kelvin second per joule. The experimental thermal resistance was found by the assumption that T block did not change with time in steady state, and thus the heat transfer rate due to ambient heating was set equal to the heat transfer rate due to air. The uncertainties were calculated via EPA. and the values at 50 and 80 psi are significantly lower than the theoretical and outside of the specified k equals 2 uncertainties.
Thanks, Anna. The system cooling equation for the time response was found using a York regression for each trial. Here are the plots, tau and beta parameters, and their uncertainties for 50 psi. Strangely, as seen in the top plot, our transient data set begins with what is basically steady-state data. Therefore, only the true transient portion of the transient response, from about 400 to 500 seconds, as seen in the lower plot, was used in the York regression. It can be seen that the system cooling equation was found to be a good fit for the segmented data. Here are the plots, tau and beta parameters, and their uncertainties for 80 psi. Only the linearized portion of the transient response, here from about 0 to 450 seconds, was used in the York regression. It can be seen in the lower plot that the system cooling equation found was a good fit for the segmented data. It is important to notice that while for the 50 psi trial the latter section of the data was used, here in the 80 psi trial the first part of the data was used. This is probably due to a combination of error in the data collection, as well as the assumption that perhaps the 80 psi trial had approached steady state much more rapidly than the 50 psi states. The effective masses of the load were calculated for each trial at the transient state. Assuming that the heat transfer rate due to ambient heating is 0, the overall energy balance reduces and can be rearranged to find the mass of the block experimentally. The mass of the block was measured in lab to be 0.4825 kilograms. As can be seen in the error column of the table, because the error values are larger than the uncertainties calculated using EPA, we are not confident in our experimental effective mass values. Our 80 psi trial, however, was more accurate than the 50 psi trial. These large errors are likely due to a combination of errors during data collection as well as sensor uncertainties. Here are our conclusions. In conclusion, we were able to successfully characterize the vortex tube relationships. However, our data did not line up with the expected theoretical values or uncertainties. One big indicator of this was that when we were segmenting the transient data to generate the system cooling equations, the back half of the data was used for the 50 psi case, while the front half was used for the 80 psi case. Looking at our data, it seems that the data collected for the 50 psi case is flawed, as having a steady-state portion in a transient data set is counterintuitive. We believe that this issue might be due to us forgetting to cover the aluminum block with a styrofoam insulation during the beginning of the 50 psi trial. This would have caused it to take longer for the block to cool, which is perhaps why we initially see steady-state data in this trial. Hence, the error in our experimentally determined values, as well as the counterintuitive data set just discussed, indicate that we need to collect new data in the next experiment in order to more accurately characterize the refrigeration system. Here are our references, and here is the honor code. Thank you. We will now be accepting any questions.